Welcome back, focused learners. Today, we're diving straight into an explainer on a topic that is just quietly revolutionizing modern medicine. We're talking about agentic AI in healthcare. If you've ever found yourself wondering how we move past simple AI chatbots to build genuinely autonomous systems for high-stakes medical settings, well, you're absolutely in the right place. Let's demystify these incredibly complex systems together, shall we?
So, here's our roadmap for this explainer. First, we'll look at the AI agent evolution. Then, the anatomy of an agent. Third, healthcare AI in action. Fourth, powering agents with Azure. And finally, building your first agent.
Okay, let's kick things off with Section 1, the AI agent evolution.
Okay, let's dive into this. You know, healthcare workflows are incredibly complex, highly regulated, and literally interconnected at every level. A basic chatbot? It just doesn't cut it for real-world clinical workflows. We really needed an evolution. Now, we started with basic large language models, right? LLMs. These are basically just text generation engines. You ask a question, you get text back. But in a hospital setting, you don't just need text, you need action. As we move down the evolutionary line, we add stuff like retrieval-augmented generation to fetch specific documents. But the real game changer here is the agent layer. An agent adds tools and planning. It doesn't just talk. It actually thinks about how to solve a problem and uses external tools to make it happen. And finally, at the system level, we achieve full workflow execution. We've literally evolved from a digital encyclopedia into a fully fledged digital clinical assistant.
Moving right along to Section 2, Anatomy of an Agent.
To really grasp how these systems pull this off, we kind of need to look under the hood and dissect their biology. Because honestly, it's a lot like a biological organism. An AI agent relies on specific, interconnected organs to function. The orchestrator, that's the brain, the central controller breaking down tasks and managing the execution order. The LLM acts as the reasoning engine inside that brain. But an agent also needs hands to interact with the real world, right? Those are the tools, like API connections to electronic health records or medical calculators. Then we have memory, which functions exactly like a hippocampus, storing the conversation history and all that vital patient context. And finally, and this is absolutely crucial for healthcare, is the safety layer. Think of this as the agent's immune system. It rigorously guards against hallucinations, unsafe clinical recommendations, and privacy violations using some very strict validation rules.
Now, what's really interesting about this architecture is how perfectly all those biological metaphors map onto the rigid technical side. The data flow is fascinating. You've got the user and external systems feeding data straight into the agent. Right in the middle sits the agent brain, leaning heavily on its LLM-based reasoning engine. Notice how short-term and long-term memory directly feed into this brain, constantly providing context. And then there's the tool invocation layer. This is where the magic really happens, folks. The brain decides it needs more information, so it reaches out via API calls or function calls directly to external databases. The data flows seamlessly from the user, gets reasoned over by the brain, and ultimately triggers real-world tools.
But how does that brain actually process a specific task? Well, it runs on a continuous cognitive loop controlled by our orchestrator. It breaks down into 4 steps. Step 1, observe the input, say a patient's symptoms. Step 2, think about what this actually means and what medical knowledge applies here. Step 3, plan out a sequence of actions, which might be retrieving medical history or calculating a risk score. And step 4, act, by executing those planned steps using its tools.
And the wild part is, this isn't just a one-and-done process. It's a constantly repeating cycle. After the agent acts, it hits this crucial reflect phase, looping right back around to the observe phase. It asks itself, did that API call actually return the right lab results? If the answer is no, it thinks again, formulates a brand new plan, and acts again. This continuous reflection loop is precisely what elevates an agent from being just a simple script to a truly dynamic reasoning engine that can handle the sheer unpredictability of medical data.
All right, let's jump into Section 3, Healthcare AI in Action.
So far, we've only been looking at the anatomy of a single agent. But what happens when we zoom out to the massive, complex scale of a modern hospital environment? A hospital isn't run by just one doctor doing absolutely everything, right? It's run by teams of specialists, and AI is scaling in the exact same way through multi-agent systems. We're talking about a network of specialized agents that coordinate to resolve highly complex, integrated tasks. Think of it like a biological tumor board. You'd never rely on just one doctor to diagnose and treat a complex cancer. You bring together a radiologist, a pathologist, an oncologist, a surgeon, the whole shebang. Well, in a multi-agent system, you have a radiology agent, a pathology agent, and a triage agent, and they are all consulting together via a central orchestrator to propose one integrated treatment plan.
And this brilliantly illustrates how tight that coordination really is under the hood. At the core, you have a selector group chat. Here, a planning agent is actively coordinating with a medical support agent, a monitoring and diagnosis agent, and administration agent. When a user submits a query, it doesn't just ping a single bot. It hits this group chat where the agents are effectively talking to each other. The medical agent might be busy pulling symptom data, while the admin agent is off checking billing codes, and they're all securely pinging a mock database in Azure OpenAI to format one comprehensive, highly accurate response for the user.
To really ground this in reality, let's walk through an emergency response workflow. Imagine a patient arrives in the ER. The system doesn't sit around waiting for human bottlenecks. A lab agent and a radiology agent kick off parallel processing the very second data is available. Then, an AI diagnostic agent instantly combines those results. If it spots a critical condition, the system immediately triggers the pharmacy agent to start prepping the necessary medications, all while blasting real-time status updates to the attending physician. This kind of parallel multi-agent coordination, it literally saves crucial minutes when lives are on the line.
Which brings up a pretty vital question. This architecture sounds absolutely incredible in theory, but where does this actually live and scale out there in the real world? How do hospitals actually host these massive, high-stakes intelligent systems securely?
Which brings us to Section 4, Powering Agents with Azure.
To make multi-agent systems a reality, we absolutely need enterprise-grade cloud infrastructure. AI in healthcare requires architecture that is highly compliant, scalable, and rock-solid secure, which is exactly where Microsoft Azure comes into the picture. Let's break down the core components. Azure Kubernetes Service, or AKS, is your heavy lifter. It runs the microservices and hosts our AI agents so they can seamlessly autoscale during, say, a crazy busy ER shift. Then you have Azure Functions handling event-driven compute. That just means they only wake up and only cost money when a specific event triggers them, like a new lab result dropping. Azure Event Hub acts as the ingestion engine, managing massive, real-time data streams from hospital IoT devices and patient wearables. And finally, Cosmos DB is this lightning-fast NoSQL database storing the agent's memory and patient interaction data with incredibly low latency.
Finally, Section 5, Building Your First Agent.
Okay, it's time to put on our builder's hats. Let's move to and see how this builds out in 4 clear practical steps. Step 1. You build the agent logic. This means defining the exact task, like, say, building a triage assistant, and writing out the strict input and output schemas. Step 2. You prepare the Azure Machine Learning Model. Here, you train your disease prediction model and register it securely in the cloud. Step 3. You deploy that model as a secure API endpoint, giving your agent a way to actually talk to it. And Step 4. You test the workflow. You punch in some sample patient data and just watch as the agent prepares the payload, calls the API, and fires back a medical recommendation.
Following that flow in action, picture new patient data entering the system. It hits the application logic of your agent, which instantly routes it up through an authentication layer because, let's be real, security is paramount in healthcare. The data, bundled up with message IDs, goes right into the inference engine, where your newly trained ML model lives. The model spits out a predicted outcome, which then cascades back down through the application logic, gets logged for strict compliance, and finally results in a concrete action. It forms this beautiful, complete, closed-loop pipeline.
But as we all know, the real world is messy. Data gets dropped, networks fail, and that is exactly why we have to emphasize validation and error handling. Remember our agent's immune system from earlier? Before an agent ever makes an API call, it has to check for missing fields. It must be explicitly programmed to handle invalid patient inputs gracefully. If the Azure ML endpoint times out, the agent can't just throw its hands up and crash. It needs a hard-coded fallback response to immediately alert a human clinician. In healthcare, an unhandled error isn't just a software bug, it's a potential patient safety incident. I want to leave you all with this final provocative thought. As you consider building these incredible agentic AI systems yourself, ask yourself this. What specific failures could happen when your code hits a chaotic, real-world hospital floor? And more importantly, what technical safety checks are you going to build into your orchestrator before you ever trust the AI's output? The technology is absolutely here, but the responsibility of implementing it safely, that lies entirely with the architects building it, with us. Thank you so much for joining me on this explainer. Keep learning, keep building, and I'll catch you in the next one.